Chapter 6 is about applications of the integral. Well, so in Calc 1 you covered a few applications such as finding the area under the curve, which ultimately that's where everything stems from. You know, that's the definition of the integral, the area under the curve between the points A and B. Alright, and then what else did you do? I believe you did volumes of solids of revolution by shell method, by the disk method, and most likely as well you did, what's it called?
The shell?
Yeah, the shell, the other one, cross-sectionals, right? Cross-sectionals. And I think that was about it in terms of the applications of the integral. So we're going to do another application for lengths of curves. And well, so let's draw a picture. Let's draw a picture here. And so let me draw just a very generic graph, you know. And well, so the arc length, so this is f of x. So the arc length here is the distance, so you can think of a particle traveling from this point A to this point B. In a very similar way for the area under the curve, well, but in this case we're looking at the arc length. Alright, so, well, how are we going to define this arc length? Okay, let me go back a little bit to something we did in Calc 1. Alright, so in Calc 1 you did the following. So you found the area under the curve. Okay, it's not working. For whatever reason, not working. Okay. Oh, perfect, it's working. Okay. So, the area under the curve. Why is it not working? Oh, perfect. What? Interesting. Oh, okay. I think it has bounds or something.
Try using white. Try using the color white. Maybe you just can't see it.
Maybe something clearer. Oh, there's bounds. I see. I was trying to do over here. Yes. So, in Calc 1 you did the area under the curve by slicing rectangles, right? So that was the approach. So can you see anything? You can barely see it, right? Okay. Let me lower.
That's better.
That's much better, right? Okay. So of course this gave us only an approximation in the area, because this rectangle, that rectangle, that rectangle, that rectangle, and notice how this area right here, right there is left out. So it's not an accurate value for the area, right? But the argument here was that if you added the area of infinitely many rectangles, you know, you make a more refined partition of the region for which you want to find the area under the curve. So in a similar way, we're gonna use a very similar argument to define the arc length. So let's see. Let me go back to arc length. So, oh, much better, right? Okay, so the idea here is that we want to find the distance from A to B. That's what the arc length is. And of course, one way to find that length is, well, I guess the linear distance right here. Well, that's to begin with. But I mean, look at that curvy distance there. So that's not an accurate result. So no, we're not going to do it this way, unfortunately. Well, so what we're going to do, okay, how about we do instead this distance right here plus that distance there plus that distance there. Well, that gets closer, but it's still not quite, right? So, but what about this? This 1, 2, 3, 4, 5. Well, it's getting closer, but still not quite. But I mean, I think you see where am I going with this. So in the same way that we were adding the areas of more rectangles, infinitely many, well, we're gonna add infinitely many of this lengths, and that's going to give us the arc length for the given function. All right, but in this case, in the case of the area, you got one rectangle as a sample, as a partition, and then you did the delta x, the sigma, and then the Riemann sum, and then you turn that into the integral. We're going to use something similar, but in this case, it's not going to be the area. Instead of the area, okay, let me take only one partition, a very generic partition here. So this distance right here. All right, so that distance there will have two components. A delta x component and a delta y component. That's the displacement in the x direction and the displacement for the y direction, which is delta y. So that's what the particle is doing when it's in this kind of motion. It's being displaced in both directions. And of course, that distance right here will be our L, which will be our arc length. All right. Okay. So let's start by finding that distance. Okay. And all you can do for this one is use, well, not the distance formula, but notice how this gives rise to a right triangle. Essentially, we have the lengths of the sides, and we want to find the hypotenuse. Which theorem actually gives us the distance or the length of the hypotenuse given the two sides? Pythagorean theorem, right? So Pythagorean theorem, which says c squared equals a squared plus b squared. But in this case, well, the c squared is the length L squared equals delta x quantity squared plus delta y quantity squared. And if we want to solve for L, take the square root on both sides. I know there's a plus and minus involved, supposedly, but in this case, since it's a lengths are positive, so we don't need to use that plus minus. All right. Now, how are we going to go from here to finding the arc length, to prove the arc length formula? Actually, I believe the formula is right below. Is it, or it's not? No, it's not. I didn't write it. All right. So, well, somehow we have to make sure that we end up with a differentiation operator that involves for the u du. But I mean, we have only delta x and delta y, so somehow we need to end up with a delta y over delta x, which is in infinitesimal form, the dy dx, which is the derivative, all right? Well, how are we going to do that? Number one, okay, let me go back to yes, I'm going to use a brighter color here. So, okay. For example, x cubed plus x squared. Okay, let's factor this binomial. How do we factor that binomial? Factor out the x squared, the GCF in this case, right? So x squared is the GCF, that's x plus 1, all right? In the same way that, of course, maybe x to the 7th plus x to the 4th, factor the x to the 4th power, times x cubed plus 1, all right? That's the GCF. All right. What about this one? x squared plus 4. Can we factor that x squared plus 4? X plus 2 squared. Well, I mean, that's just rewriting the 2 as a, I mean, the 4 as a 2 squared, which doesn't really, but that's not really like factoring the polynomial itself, right? So apparently we don't have a GCF in here, right? But, okay, check this out. I'm going to factor out an x squared. Oops. How about this? You know, I think it works. And this is the trick that we're going to use to derive a formula for the arc length in our derivation here. All right, so what we're going to do here, I'm going to factor out L equals to the square root of delta x squared times 1 plus delta y quantity squared over delta x quantity squared. All right, sounds good? Okay, so in this case, inside of the radical, what do we have? We have the product of two factors. By the product rule of radicals, we can split this radical as the product of delta x squared times the square root of 1 plus, this is the same as saying delta y over delta x quantity squared. Okay? And of course, from here we can simplify the delta x squared, cancel that with the radical. So that's going to give us delta x times the square root of 1 plus delta y over delta x quantity squared. All right. Now, do you see that delta y over delta x? So we're doing all this process for only a sample of the partition that later we're going to add infinitely many of those in order to use that argument and come up with an integral form for more practical terms for this. So this is what we're going to do. So that's one length. What we're going to do here is, well, find the length of infinitely many of those. Well, so I'm going to add, that's an n or k equals 1 to n, or no, it's n actually. Okay, so this is n equals 1 to k, and well, this will be the square root of 1 plus delta x, delta y rather, and I'm going to put a subscript k. That's for the kth length, because we're going to add the first length, the second length, the third length. So this sum, this sigma symbol means to add, and I'm going to add the first length and then the second and all the way to the kth length. All right, and then from here multiply by delta x sub k, the for the kth one. But of course that's adding a finite number of them. But of course if we add only a finite number like 5, well, 5, we saw that 5 is not going to give us the actual length. 7 is not going to give us an actual length either. Even 100 is not going to give us an accurate length. So what we're going to do is turn this into a limit of the sum as k approaches infinity. Well, now that we're using an infinite limit, a limit approaching infinity rather, we can just turn this into our integral from a to b of the square root of 1 plus delta y over delta x is the slope of the secant line, but when we add infinitely many of this, that really turns into the derivative dy dx times dx. All right. Another form of this one is, and I think it's more compact, f prime squared. Alright. And that's a formula to find the arc length. I don't always do this kind of derivations proofs, but I think this one is a fun one to do. I think it's not, especially because most of the proofs for the material that we covered this semester in this class, some of them require a little bit more advanced mathematics. This one is fine. This one is a good one to do. So that's how we find the arc length. So how about we look at one example. Let's find the arc length for this given function f of x equals to 3/2 x from 0 to 4. Alright? Well, in this case, make this a little bit bolder. Okay. So what do we need? So we need to identify, of course, our function. Right? Okay. Let's identify our function, and notice for the derivative, or not for the derivative, for the arc length, L it needs the derivative of the given function that we want to find the arc length for. So let's go ahead and find the derivative of this function. So let's do this on the side. The derivative of x to the 3/2 f prime is 3/2. X to the 3/2 minus 1, isn't that 1/2? Which is the same as saying 3/2 the square root of x. You can leave it in radical form, or you can leave it in rational exponent form. Either way, it's fine. Alright, well, so now we have all the elements that we need to find the arc length for that given function within those limits. So that's the integral from 0 to 4. What happened here? 0 to 4, square root of 1 plus that derivative squared, which is 3/2 root of x with respect x. Now be careful with everything that's going to happen here. Number one, because this 3/2 square root of x, the whole thing is inside of the parentheses, this square right here will affect both the it will affect both the 3/2 and the square root of x. So let's see. So that's going to be the integral from 0 to 4 square root of 1 plus 3/2 squared. That's going to give us a 9/4. And what's the square root of x quantity squared? That's just x. All right, with respect x. Well, let's have a look at this integral. Any ideas on how to evaluate that integral?
Separated?
Separated, you mean the square root of 1 plus the square root of 9/4 x? Careful, we cannot distribute a radical over a sum or difference of terms, right? Tiffany? Use substitution? Yep. Use substitution where our u equals to the quantity inside of the parentheses du equals 9/4 x dx, and of course Oh wait, no, it's just 9/4. 9/4 dx. And dx equals to 4/9 du. Alright? Okay, here's the thing. You can go about the substitution, integrate, and then back substitute for u, and then take a few minutes to evaluate upper limit minus lower limit. However, my advice is to change the limits of integration also to the world of u. So what we're doing, every time we do a u substitution, we are given in a way a complicated problem in the world of x. We send it to the world of u in a simpler way, compute the problem or solve the problem in that world, and then undo the substitution to go back to the original world of x. However, to be consistent with this kind of substitutions, technically we also have to change those limits of integrations to their equivalents in the world of u, which is what I'm going to do here. And to do that, so let's do u of the evaluated at the lower limit and u evaluated at the upper limit. So that is 1 plus 9/4 times 0. That's simply going to be 1. And 1 plus 9/4 times 4. Well, this is good because the 4 is canceled. That's going to be a 10. All right. Oh, come on. That's supposed to be a 4. So, our new integral in terms of u will be the new limits are going to be from 1 to 10, and that's the square root of u with respect u. But don't forget that factor 4/9. I'm going to write it just outside of the integral. That's fine. We can do that in that same step. Well, of course, we cannot just integrate the square root of u. We need to rewrite this in rational exponent form. To do that, okay, let's 4/9, the integral from 1 to 10, u to the 1/2 du, and just use the general power rule. The integral of u to the 1/2, okay, that's 4/9 first, times u to the add 1 to the exponent. Is that 3/2? Evaluated from 1 to 10. Alright, so the advantage, you'll see the advantage of changing the limits of integration to the world of u, because in this case we can just use the fundamental theorem of calculus from here, from the u's, instead of having to go back, substitute, and write a really big expression. Of course, if you want to do it that way, that's fine with me. Just keep in mind that that might take a little more time. Okay, so dividing by a fraction is the same as multiplying by the reciprocal. 4/9 times 2/3, and that's u to the 3/2 evaluated from 1 to 10. And well, so 4 times 2, that's 4 times 2, that's 8. 9 times 3, is that a 27? So 8 over 27, u to the 3/2 from 1 to 10. And let's just do upper minus lower limit. And that's simply 10 to the 3/2 minus 1 to the 3/2. Instead of doing all that back substitution. Alright, and well, that's our first final answer. So we need to simplify this a little bit. One thing to recall from intermediate algebra, so it's this property of rational exponents. Whenever you have x to the m over n, this is the same as saying the nth root of x to the m. The denominator of the rational exponent gives you the index of the radical. Another version of this one is, I think I'm gonna leave it this way. I'm gonna leave it this way, but I'm gonna show the other version, the n root of x, the whole thing to the n power. So depending on how we want to compute this, well, we may use one or the other. All right, so let me rewrite this. Well, of course, 1 to any power is simply 1. But in this case, this is the square root of 10 cubed minus 1. But this 10 cubed can still be simplified, so we can compute that square root if we rewrite it in the following form. So this is the same as saying 10 squared times 10. Do we agree with this? And then from here, let me highlight the perfect squared. That's the perfect square that we can factor out, and well, that's going to be 8 over 27 times 10 root of 10 minus 1. Alright, and that's the final answer for this. So this is how we need to simplify these numerical values for this kind of exercises. So, and that's both for my MATLAB and for the exam as well. So because sometimes my MATLAB is a little bit picky with the form for that you input as your final answer. They're going to tell you all your answer is correct. It's not written in the most simplified form. So, all right. And yes, for this kind of exercises, these are the kind of answers that we're going to get, like really weird numbers. All right. Okay, so let's see. Let's have a look at another example. So for the next example, example 2, find the length of the arc of the curve y equals x cubed over 6 plus 1 over 2x between x equals to 1 and x equals to 2. However, how about we take a 10-minute break and we do this one when we're back?